So let's continue. And until now, we have had filters working directly in the spatial domain. You can see that if I modify something on this pixel or taking these in pixels together, then I get the results. Frequency domain filters requires some extra transformation, and you will not easily recognize your image after the transformation. So first of all, let's look at the Fourier transform, which is our way to go from spatial domain to frequency domain. And yeah, then you get some ugly equations. Probably you have seen them somewhere during your math classes. But often when you look in the math class, your Fourier transform is only one-dimensional, but actually the theory expands to any dimension. So you can do a Fourier transform in 2D, you can do it in 3D, if you like. It just takes longer. And there is a forward transform and an inverse transform bringing you back to the original image. So ideally, when you go one way through the transform and back, you should have the same image. But we're not interested in doing just that. I come to that a little bit later. And again, this equation you don't have to implement yourself because many smart people have been working on it. And I don't know if it was in the 70s already. They developed this FFT, fast Fourier transform, which is the transform type you use in computers today. So there is a lot of prepared codes. There is in Python, C, etc., different libraries that compute the Fourier transform for you. And even in different flavors, depending on the shape of your data. So, some mathematical features of the Fourier transform. So if you have the Fourier transform of two signals, first I have the sum of two signals. It is the same as if you take the Fourier transform of the signals individually and then sum those two up. And looking at that, we have signal 1, signal 0, and signal 1. And if we sum them, it looks like this pattern here. And looking in the Fourier space, you can see that this is a low frequency signal and this is a high frequency signal. And if you look at the Fourier spectrum here, you can see that the two peaks that you have, one is for positive frequencies and the other is negative frequencies. So the Fourier transform is always showing positive and negative frequencies. And the middle is then the 0. So you get always a mirrored effect here. If you have the higher frequency, it goes further away from the 0. And then if you do the sum, you can see that it's actually the combination of the two of them like this. And if you would take the Fourier transform of this one, you would get that too. Yeah, so this is a very basic demonstration of how frequencies are put together with the Fourier transform. More interesting than the summing is actually the convolution. Because if you convolve two signals in the real space, then it's the same as if you multiply the Fourier transform of the two signals. So the convolution is a quite expensive operation, as you have to repeat around the kernel all the time for each pixel. And here instead, you can just multiply, which is a pixel by pixel operation. The other way around also works. So if you do a convolution in Fourier space, it's the same as a multiplication in the real space. That one is less used in filtering applications, but just wanted to mention. So let's look at some images. We have this picture of some juggling balls. And we add noise to it. So this is the noisy image that we want to look at. And looking at the Fourier transform of these images, you can see here that we can use in NumPy. There is a sub-package called FFT, and there you use FFT2 for the two-dimensional Fourier transform. And there is a computational reason that when you just compute this one, you will have the zero frequency up in this corner and the first negative frequency down in this corner. And it's not so easy to look at because then you have all the intensity around the edges. So what you can do is to apply this FFT shift, and then it reshuffles the quadrants, and you have the zero frequency straight in the middle. Now you can see that there is a lot of intensity in the middle because we had large flat areas, which is essentially no frequency as a zero frequency. And then along the main axis, you also have a rather high intensity. Then you can see here there is some fuzzy cloud around which decays towards the edges. That tells us that we have most of the frequency information or energy in this image is centered around the low frequency. And looking back, you can see there are large flat areas in the image, and the large flat areas are the low frequencies. And then there is a little bit of edges, but not so much. Looking at the noise, there is not much difference actually between the noise in the frequency space and in real space. So it's just, in this case, it's a white noise. White noise means it covers all frequency equally much. So this is what we see here. It's just noisy at some amplitude. And then if we look at the two images together, so we look at the sum, you can see that now it's getting a bit more noisy, and also that the information you had here is less pronounced because now it's hidden in the noise amplitude. And this is something we want to look at. So let's try to apply a wild filter. In this case, I want to apply a filter that focuses on the DC components in X and Y. And with that, I create this filter window. So I just filter out, saying everything outside of this cross is 0, and inside I keep the information. When we apply this filter, the first thing you see is that the noise actually has removed, because we cut away a lot of areas in the spectrum that mainly contain noise, or where the noise was dominant. But the other effect is that you see this stripy, textile-like pattern, and that is because we now also enhance only those directions vertically and horizontally. And that is what we see here now as this pattern. So when you apply a filter in the Fourier domain, you have to be aware which kind of structure you promote. Otherwise, you can get this kind of effect. But you can, in principle, also apply a Gaussian filter. And typically, when you have a very large Gauss kernel, say 100 pixels wide, then it takes a very long time to compute. In the Fourier space, it's very easy to do it, so that would be a possibility. And then you would have the Gauss filter applied in the frequency domain instead. So another filter which is a bit tricky maybe in the beginning to work with is the Wiener filter, and that is a signal optimal filter where you have a filter the point spread function of the system, and you have the power spectrum of the signal, and you also have the power spectrum of the noise. This is not so easy information always to get, but by doing this, we can even do deconvolution. So I mentioned before that the optical system can introduce blurring into your images, and with this equation, I must say, in theory, you can do some basic deconvolution, so take out the blur caused by the optical system. But as soon as you divide by some signal, you can get a quite unstable solution, and that is often what happens when you try to do deconvolution. But what we can do instead, a very special case, is to do denoising with the help of a simplified Wiener filter, where we have the power spectrum of the signal, and in numerator and denominator, but in the denominator we also add a sigma for the noise variance. And the effect now is that if the amplitude of the signal spectrum is much greater than the sigma, then the filter function is equal to 1. And if the power spectrum is much less than sigma, then the filter function is equal to 0. And we need to measure this PS, which may not be so easy always, because we may not have the original. We only have noisy image. But anyway, let's try. We have this noisy balls again, looking at the filter function, and then I compute this G function. I should have added titles on these blocks, but I compute the filter function, and you can see now that in the central part it is quite much ones, which is good because we want to preserve the image information. And then we go towards the edges, it gets more and more going towards 0. And the effect of that filtering is that we take out the noise, and we can also have less of these textile shaped artifacts. And looking at the histogram of the noisy image, it looks like this, where you more or less you can see if it's dark or bright. And in the filtered image, you can see that there is some dark background, but there is also some 2 different types of regions within the image. So this is a way how you can do the filtering. It's a very simple example. If you really want to work with Wiener filter, I suggest you really go into deeper examples, and are even implemented to some degree in Scikit image, I think. But this is the basic principle of the Wiener filter, and it can be very powerful if you put them in the right context. So another thing we can do with the help of the Fourier space is looking at orientations. And looking at the spatial frequencies and the orientation, you can see that if you have ribs like this in the horizontal ribs, you can see that in the Fourier space it turns out as 2 dots which are aligned in the direction perpendicular to this pattern. And if you have 30 degrees, you can see it's also tilted a bit, so it's always the same. So this line is parallel to that line. And if you do the 60 degrees, it's now you have the line like this. 90 degrees, then you have the 2 dots in this direction instead. So with that, you can actually detect orientations, or you can do orientation sensitive filters. And this is something I did in one example to remove stripes in images. So this is an image measured at the synchrotron, and there you have a pattern which was at that time floating, so it wasn't stable this illumination, and I got these stripes in the image. And looking at the frequency filter, frequency domain, I could see that there was a little plume going out in this direction, and that plume I identified as these streaks that we looked at. And knowing now that streaky patterns, which have an orientation, they can be identified in the Fourier spectrum, then I created a kernel looking like this. So I really tried to cancel. So everything red is 1 and blue is 0. So I just canceled out what's happening in this little area here. And after filtering, the image turned out like this. And the effect of that, so this is a single projection from a tomography. The effect was, before filtering, we have this cloudy background in the air. And after applying the filter, I got pretty flat background, and that was what we wanted for our investigation. So this is a way how you can actually see how changing in one domain, in one place, can have great impact on the further processing. Then there is a bunch of functions related to the filtering. So we have in the image and scikit image, we have a lot of functions. We have convolve, median filter, we have the Fourier transform in the NumPy. And when you do the Fourier transform, you actually work with complex numbers. So then you need to work also with the absolute values, looking at angles, and also looking at the real imaginary parts of the complex numbers. So now we have talked mainly about the filters in linear spaces, but now we go one step further, talking about scale spaces. And the idea is that when you do the filtering on the full image, you may filter some structures pretty well, but it's hard to get larger structures or larger variations. And with that, you can work with something called a scale pyramid. In, say, sometimes you explicitly produce this pyramid. Other cases, you have the mathematical framework that handles the pyramid. But the idea is, with the pyramid, every time you go one level up, you do a downsampling, so you reduce the image by maybe a factor 2. And then you go up to smaller and smaller features. In the end, the top level doesn't say much, but here you can still see something. And the first approach to do it is working with something called wavelets. And that is a transform that transform the image into two parts. So you have your signal, and after the wavelet transform, you have one part is the detail, and one part is the trend. And the trend looks like what you had originally, and the detail is essentially a high-pass filtered version of the image. Every step, you also shorten the image information to the half. So you have one half is now trend, and the other half is detail. And the good thing is, with this wavelet transform, which requires you to use some specific base functions, you can actually go backwards too. So it's not that you destroy it by going down these scales, but you can actually come back. And wavelets can be used for noise reduction, analysis. Typical wavelet analysis is in seismic analysis, or I think also in electrocardiograms. They have done some wavelet analysis to see and look for patterns in these signals. It's also used for segmentation and compression. And in particular, compression is the compression algorithms used in JPEG. They are based on wavelet theories, but I think they have drifted away from the wavelets themselves. So, what does it look like in reality? We have a one-day signal, which is a sine and a square wave, and that is split into one part, which is the trend. You can see it's less noisy, but also shorter, and a detail, which is just the noise, essentially. Then you go on, another decomposition, so now you go to the next scale, and here you can still see that there's a sine, and the wiggle is still not very understandable. And the last part can do another one, still more or less looks like the original signal, but much, much smaller. And this one was used with a base called Simlet4, and there is large catalogs of different transforms, and depending on your application, you have to specify which of these wavelet bases you use. If we do it on an image, it actually also goes scales in dimensions. Then you do instead, you take your image, and there you have first you have the trend, and then you have horizontal detail, vertical detail, and diagonal detail. And that is again split down. So you take the trend and do the same split, do the trend, same split, and so on. And in images, it looks like this. So we have the original image like this, and it's split into 4 parts. The diagonal trend is barely visible. You can see a little bit about the horizontal features, a little bit about the vertical features, and then if you do the transform again, you can start seeing different features in the image, and then one step more, then we have the trend, and you can see now that we have the horizontal part of the circles and the vertical part of the circles are easily you can see them. And this is a tool in order to get the filtering done, and here is an example how to do the noise reduction. So what we do is we do first the decomposition to some level. In this case, I only do one level. And looking at the detail and the peaks that go outside of some threshold level, they will be kept, and everything else will be set to 0. Because the peaks that are going outside, they actually can correspond to some real information. So we want to keep. The rest, the ripple, we don't want to have, so that we just reject. So the new detail image looks like this, and then when we combine it back, you can see that we have reduced the noise quite a lot, but not fully. So this is an approach how we can do the filtering. Of course, again, there are much more refined ways of doing it, but then I would probably have to spend a whole lecture on only that. So this is just giving you an idea what the wavelets, how the wavelets can be used. Yes?
Why would the peaks be corresponded to signal?
Why? In this case, it's actually not that obvious, but usually the idea is when a peak is strong, then it actually has a real interpretation. If it's weak, then it's more likely that it is a noise part. Yeah, and usually you can also say this level, given the signal to noise ratio in the image, you can also tell how much you should press it together or take it apart. And here is an example where I used this approach. I believe I did a couple of levels, because otherwise it wouldn't turn out like this. But it's a quite noisy image, also even with line artifacts in it. And then I run the filter. It does quite a heavy filtering in this case. And you can even see that there are some wavelet artifacts, and that's also the same kind of artifact you can see in JPEG compression images. When you have a heavy compression, you can have around some small features in the image. You can see how it starts rippling and ringing. And that is when the compression was taking away too much information. Then we have a next step is doing a lot of math. Then we go into parameterized scale spaces. And with that, we use partial differential equations to do the filtering effect. And here are some examples where we have an original measured image using one filter called diffusion filter, and the other one is a total variation filter. And you can see here that these filters, they are capable of taking out a lot of this coarse-grained noise and still maintain the edges in the image. And to remove that using a normal convolution filter, you would have very smooth edges and you would lose information. For example, about very narrow throats, they would be overwritten if you use a normal convolution filter. And let's see, so here we start with a diffusion filter, and that is originally defined based on the heat transport equation. But the problem when you apply the heat transport is that it goes to equilibrium, which is a completely flat image. So it doesn't help us a lot. You can see here how it vanishes and goes out into nothing. And for that, some work was done, and they added diffusivity control function where you have near the edges no diffusion, and in flat regions you have diffusion 1. And that can be defined by this control function, which is a very steep function that goes from 1 to 0 at some threshold level. Here we have to define the steepness of the threshold function and also at what level, so how strong gradients are needed in order to say that it's a 1. This, again, must be done with some analysis. So if we have an image here and compute a diffusivity map, we actually have to look at the gradient image or even the smooth gradient image. And again, using the approach, maybe using the histogram, looking at where do we have the turning point, which gradients can be considered being edges, and which gradients can be considered being flat. And the edges are much less frequent in the image, so it would be some kind of the outlier part, outlier tail of the histogram. So we come more or less back to a similar criteria as we have here. So yeah, and then they added this a Gaussian filtering on the gradient to make this diffusivity function more stable. And in the end, we have an example here. This is the same image as I had before, but this time we can actually do the smoothing. And in the beginning, it doesn't look like it happens a lot, but the end result is actually, you can see in particular in this region here, that it starts getting more patchy and smooth. So this was used a lot early 2000s, and mid 2000s they started doing a lot of math and came to something called the total variation filter, where you do an optimization based on the bounded variation, which is the sum or integral of the gradient squared, and also some fidelity, so comparing the original with the filtered image. And that results in something called the inverse scale spacer or scale space filter, or a framework for that, which instead, as the gradient filter, looks at small features and trying to remove them. The scale space, inverse scale space, goes from the large structures and add smaller features. So that filter actually turned out to be very well used, at least in my group. We have used it a lot. And it again turns into a differential equation system that is filtered, that is implemented for the filter. And here you can see how the filter iterations act. And you can see that it's smoothing very well. And where do I have my pointer? Here. And you can also see that even though you have a very strong smoothing effect, the edges of the structures, they are very sharp still. And that is often what we want to maintain. At some point, this filter actually overfilters because you lose structures, so you have to experiment a little bit, play and see to what degree you want to filter. Then yet another approach is called non-local means. It's a completely different approach actually. And the idea is that normally when you do a convolution, you just run over the image and filter based on a neighborhood. In the non-local means filter, instead, you're searching the image for patches that have similar structures. And those structures you compute the average together from, and that is the filter value you put into your image. And that is really giving also a very good filtering effect, but it's also a quite expensive filter to compute, and a couple of algorithms were needed to speed up it and make it useful. Yeah, I skipped those equations, but this describes essentially how this searching for similar blocks, how it works. And then in the end, we come up with results like this. And you have the original image, and then after applying this non-local means filter, you can really get very smooth results. It's not capable to take the ring artifacts. They are actually more or less enhanced. But it's pretty good. It's also implemented in some commercial software. And you can get some patchiness when you run this filter. There is a bit of a performance problem because the complexity is n squared. So if you have three-dimensional images, you really have to have a good strategy to work with it. Otherwise, you would have to compare every pixel with every pixel in the image, and that takes quite some time. So there you have to reduce yourself to smaller regions and patches to reduce this complexity. There is a notebook in the repository where I go into the details. If you want to go into more details about the non-local means, I did a notebook extra where you can see, explore how it works, the different components, and also the effects of the filter. Yet another filter, which is kind of an evolved non-local means, is the so-called BM3D. And BM stands for block matching, and 3D is how the filtering is done. It came a couple of years after the non-local means filter, and it's today, I would say, the best non-deep learning approach to denoising that is available. If you want to look into the deep learning approach, I would suggest you to read this paper where they give even more information about that. The algorithm for the block matching filter is a two-step algorithm. One is doing a pre-filtering to prepare the data for the true filtering. And it's first doing a cosine transform, which is essentially the half Fourier transform. And then from the frequency spaces you get, you compute, you do some thresholding in the spectrum, and based on the similarity between the spectra of all the blocks that you have collected, you can then say these blocks, they will be put together, and then we do some filtering on that. And the filtering is that you have all your patches around the image that are similar, then you bunch them together. So you had 2D, you bunch them together and get a 3-dimensional image, more or less, and then you filter in this 3-dimensional space and spread out the blocks again. And the next step, so that gives you a basic denoising, and then you repeat it, but this time based on this basic denoising, and then you do it again, the same approach, but now instead of doing just thresholding in the frequency space, you apply a Wiener filter instead and get the best result out. And here are some examples how the blocks are identified. So looking at these, I think it's from 4 different sources, yeah. So this is around some window. This, I actually don't know what it is. That one not. That is from, I think, from the Lena image. And you can see along the ridge of the nose, or the reflections on the nose, they are quite similar. So these blocks, they will be put together in one filtering batch. And then we applied it in our group on first on some simulated images to see what the effect is. So here we have a noisy image, apply it to non-local means, total variation, BM4D. 4D is because we had 3-dimensional images, so the filtering is actually done in 4-dimensional space. And then compare it to the clean image, and then we have a ground truth that we compare to. And here's another case, and the BM4D is actually the one that turned out to be the best choice also in our case. It was amazing to see what it could do on real data. Well, 3D images is a bit messy, because then you have to actually do this collaborative filtering in 4D, and that can be a bit tricky to implement if you don't find a good code for it. There are some implementations, but they are not really what I want to have, so we probably need to implement this filter in our group ourselves. And computationally, there is an implication that 3-dimensional images require a lot of memory, because you need intermediate storage for the steps. And of course, the processing time can be long. I would guess we would need a couple of hours to filter a 2K cubed image. So instead, there is, or I even heard about colleagues who spent a couple of days of filtering some data. So it can really take long time running this filter. And therefore, there also exist some implementations of it on the GPU. Unfortunately, the GPU versions are not so well parameterized. It's just a minimal implementation, and that's also a little bit a limitation on it. So this is still active, and there's still code developed. There is open source code and some, I would call it semi-open. They have delivered some binaries and some wrapping for using it in Python. And going even further, this is probably not so visible on the screen here, so you have to take it on your own screen. But what I want to highlight is, in particular, comparing these 3 down here. The upper ones, they are, no, so it's a clean, noisy, non-local means. And you can see that the non-local means does it very patchy, so the large areas, they are very smooth, but it also hides finer details. Going to BM3D, it's actually doing a pretty good job, but there are places where it doesn't work that well, particularly around the face and also along the dress here. Some of the folds don't come out well. Then there is a comparison to two machine learning based denoising, and if you look close to it, the face on this one didn't come out very well, and that's often the thing that you want to preserve very well are small details in the filtered data. And because those can be small details you want to really to follow in your investigation. And looking at this one, it actually preserves the face well, all the folds in the dress, even the corrosion up here. So this is the one that fascinated me the most. I haven't tried it myself. This is a way that we're also going to look into in the future. And now that we have this large palette of different filters, is the question which one to choose and when. So, of course, you can say take the best. So let's take the beast, the machine learning beast, and bring it in. But there are some obstacles on the way. Every filter has its pros and cons. So some questions you need to ask first is, do you have 2D or 3D data? Also, how the image is composed. Do you have very many small details that you want to preserve or not? Also the signal to noise ratio, how noisy are your images, and that also tells which kind of filter you can apply. Practical issue is which filters do you actually already have in your toolbox. That's actually quite many in Scikit image. But it may not be the ones, so you should probably try them first before you do something else and see if they perform as you expect. Then when you go to the more advanced filters, you also have to ask yourself, do you have the hardware to run it? As an example, the total variation filter I have requires 4 or 5 times the image size as intermediate storage, and even more memory hungry implementations out there. And if you have, say, a 2K cubed, that's already 8 gigavoxels times 32, because you do it in floating point. No, times 4, sorry. You do it in floating point. Then you're already at 32 gigabytes. And then you want that 4 times again. And then you have probably blown up the memory in your laptop a couple of times. So then you need to go to a larger workstation, or you have to find strategies how to split down your data in order to filter it in a good way. Then how much time you have can also be that you need to think about this aspect. In some cases, you need to implement the filter yourself, and because the filter is not available out there as open source, so then you need to spend quite a lot of time on doing the implementations. Then comes the use time. How many images do you have to filter? If you have a single image, let it run for 2 days, no problem. But if you have 1,000 or 10,000 of images, you can't spend 2 days on filtering each. Then it would be way beyond your PhD time, and probably also going beyond your postdoc. So then you have to look into what kind of filter you can use. And in the beginning, it's about testing, comparing what would be the best choice for you. So I can't give you an exact, but these are things to think about when you select your filter type. Last part today. Oh, I'm going to run over, I see. Do you mind? Okay, good. It's about enhancing and analyzing orientation. And typically, we can see here in these images, there are typical structures. In this one, you can see there are round objects mainly. In this, some hair or something like that. And the last one here is a peacock feather. And you can see in all of them, you have some very textured structures. Maybe not in that one, but there are clear orientations in it. So the question is how we can measure them. So now we are actually going over to quantifying information using filters. And looking at the gradients, we can, of course, as we have seen before, see that we have the clear sides vertically, the clear sides horizontally. Looking at the hair, you can see that we have also some preferential direction here in this area, and this doesn't show very much. And in this one, we also have some more horizontal preference. In the peacock feather, we have some diagonal structures. They come out more or less equally well in dx and dy. But this is still only intensities, and we still have to interpret. So now we want to measure the orientation of these structures. One way, as I mentioned before, would be to do it in the Fourier transform. But as you can see, it's not so easy when the images become more complicated. In the examples I showed before, we had clear ripple structures, and then it's easy to spot the two dots that correspond. But looking at this one, the only thing, if you look very close, is you can see that there is some kind of concentric ripple, and that would be for the balls. But it's not easy to see any orientations in it. Then looking at the hair, you could possibly see that there is a main streak here. Possibly there is something diagonal, but it's quite fuzzy. And from the feather, we can see that there is a diagonal orientation with some spread, but also that doesn't really give us the information that we want. So what we can introduce now is something called the structure tensor. And that is the combination of the product between the gradients in it like this. And then we have the diagonals are just the gradient in x and the gradient in y squared. And the other diagonal, we have dx, dy combined. And then usually we also apply a Gaussian filter to make it less noise sensitive. And then it turns out like this. And there is even a little function how you can compute your structure tensor. An interesting thing here is I use the Gaussian filter, and it has this extra parameter where it says order. And with that you can get, when you do the Gaussian filter, you can at the same time also get the derivative, and you decide which derivative you want to look at by this parameterization. So that's quite convenient actually. And from that, we can look at the different components of the tensor, and we see, of course, the vertical, horizontal, diagonal information. Not so much new information yet, but now if we start doing eigenvalue decomposition of this tensor, then it starts getting interesting, because from that we can compute the local coherency, which is where is my pointer? Oh, on the wrong screen. Okay, so if the coherency is 0, then we have an homogeneous region which doesn't really have any dominant rotation. If it goes towards 1, we have some rotation and well aligned in one of the axes. It doesn't say which one, but at least we have an indication in this region there is a preferential direction. And everything in between, we have a mix between the two of them. And here's an example. We can see in this image with the balls that around the edges of all the items we have a high local coherency, so there is a preferential direction in this area. And somehow I forgot to split this into 2 slides. But with the help of the components in the structure tensor, you can also compute the local orientation angle according to this equation. And then I also provided a little function for doing this. And then it starts getting fun, because the new image here actually tells us the local angle in the image. So now we have already come a step towards the quantification. So here we have pi half plus and pi half minus. So this is what you can then turn up and see which local orientation you have in the image. The balls, they're round, so they don't tell much fun in principle, but it shows at least that we have our rotations. And now let's look into these textured images, where we have the hair and the feather, and looking at what they can give us. So, looking at the hair first, the coherence image is completely yellow, which means everything is a 1, so there is a lot of local structure in it. And looking at the local angle, then it's getting interesting, because we have regions which are blue-ish, and we have regions that are more red. And looking at the histogram here, we can see that the average rotation in this image is 0, which means that there is essentially equally much of vertical and horizontal structures. But you can also see that there is a lot of angles in between. The feather is more dominant on the red side, so because we have this 45-degree dominant orientation. Apparently the eye of the feather is less structured, or it's more blurred somehow, so it gives less coherence information. And then we can see here from the histogram that we actually are around 45 degrees with this image. And with that, we can also find the maximum peak, and saying that the average direction in this one should be 0. Can agree or not agree. But in this one, it's pretty clear that it is a 45-degree rotation. And then we can look at it locally. So we take the histogram of the local places in the image. We can see this one, and that one. And we can see also that the histogram is moving depending on the local orientation in the image. So that we can take one step further, creating an image that specifies local orientations. And because the average orientation can be misleading, like we saw in this hair image, it's just said it was a 0 because that's the average of everything. So now we want to look at the local orientations, and with a couple of functions here, we can compute either an image that tells that the local orientations have some preference, and we can do also some arrow plot showing the orientation locally. So, oh yes, I talk a lot today. Sorry for that. Finally, the verification. How good is my filter? Because when you apply a filter, you do a modification to your images. And there you need to specify, or at least quantify, how much you change it. And my former boss, he was always talking, can you trust this data massage? You modify the data until it looks like what you want. And sometimes when you apply too strong filters, you actually can modify the images beyond recognition completely. And Therefore, we need a toolbox of ways to validate your filtering. So the first one is quite simple, visual inspection. It's images, so just by looking at them, you can tell good, bad. And if you can already by yourself say not good, then you have to go back and do something else. Then we can start looking at difference images, and we can even include some kind of framework for more reproducible tests about how the images work. So, looking at the difference images, we have a noisy image, and we can subtract, and that actually requires you have an original and a processed one. And then when you apply the filter, when you subtract the original from the processed, then you should ideally just get noise if you have a low-pass filter. If the filter is too strong, then you get over-smoothing, and then you can start seeing structures in the image, so then you start seeing edges appear. If the filter introduces intensity scaling, so that is when, for example, your filter kernel is not normalized to 1, then you can get intensity scaling by applying the filter. Or even you can get geometric shift, and that would be the case when you have an even filter kernel. Then everything is shifted by 1 pixel, and then you can get this kind of black and white effect in the difference. Then I have something that I named the smoke test, and that's in principle something that came from the time when I was playing with electronics, making my nice circuit, driving it and see how it worked. Some pieces got hot and started smoking, and well, then it was not good. So in principle, what it means is that you have to pull your system, or you have your algorithm where you do something, and you have to try different parameters in your filtering and see where is the filter or your algorithm performing well and where does it fail completely. Routine is first you create some phantom images with relevant features, then you add noise, then you apply your processing and measure the difference between processed and phantom, see if it's good, bad, and then you repeat a couple of times these steps to get some statistics for different noise distributions, and then you can plot and see what is the effect of different parameters, a different signal-to-noise ratio. And you can create phantoms like this, either from simulations or from geometric models. And the parameters you can play with are shape, sharpness, contrast, noise, and so on. And of course, we have data for that I talked about last week. You can have label data for where you check performance using these databases. And then I also have some evaluation metrics that I use for gray level images. One classic one that's used is the mean squared error, which is just summing all the difference between the 2 images squared and summing all up. And a more complicated one is the structural similarity image, which was introduced because that one wasn't so reliable if you have a bias only, and the image in otherwise would be okay. MSE would give you a great error, but this one is capable of seeing that it was just a bias and saying this is actually quite similar after all. Interesting reading in this paper. I think I also referenced it in the beginning. And here is a test example. So I had a test run with different phantom structures. These are, by the way, roots. So I was trying to find roots in tomography images, and I needed some tree-like structures, so I created these. Then we changed the contrast and signal-to-noise ratio. You can see here that in this case it's quite noisy, low contrast, so it will be hard for the algorithm to find it. After running, I got some response curves on the different cases. So here I played with the different voxel sizes. I also had some signal to noise ratio, and you can see that the algorithm has big problems here with the small structures, but it's more robust naturally for larger structures. So that brings me to the end, a little bit over time. But in principle, I have talked about many filters today, and you can see here the performance using different types. And also looking at the smaller details. This is the cross in the middle of the image here. And you can see how the different filters. So here I didn't add non-local means and BN3D. But you can see that the box filter doesn't perform very well for the noisy data. And diffusion filter and total variation, they do a pretty good denoising, but not perfect. Yeah, so in principle, we have looked at a lot of different filter types, and what you select, as I showed on the previous slide, depends on what you want to do with the data and what quality requirements you have and available time. In principle, you can do a lot with filters, but it's even better if you do a good measurement from the beginning, so you don't have to do a lot of denoising. But we can fix it if it is noisy. And then I reached the end. I think, yeah, that was the end. Yeah.